So I'm going to talk a little bit about today's experiment, measuring moment of inertia. But before I do, I wanted to talk a little bit about this experiment we did a couple weeks ago, testing Newton's second law. If you remember, we had an air track, and there was a pulley and a mass hanging off the side. So this is a little m hanging off the pulley and a big M on the cart on the air track. And we figured out from doing the force body diagrams that Newton's second law predicts that the acceleration of the system will be little m over big M plus little m times g. And we sort of measured all this stuff. We measured the acceleration, we measured the masses, we used a known value for g, and we used this to test Newton's second law. So now, instead of using this to test Newton's second law, imagine that you believe Newton's second law is a reasonable way to describe the world around us. Then you can turn this into a system for weighing dynamically, right? If you can measure the acceleration, then you can figure out the masses. So say you know what little m is, but you want to know what the air cart weighs. Then you can just run the experiment, measure the acceleration, and solve this for the mass of the cart. Once you've done that, you could weigh anything else that you could put on the cart by just tacking it on there, run the experiment, do the measurement, and calculate a new value for big M. That would be the cart plus whatever's on there. Now, that's basically directly analogous to what we're doing in today's experiment. So here, what we have is a rotating turntable that you can put a moment on. You can put an object on that you want to measure its moment. And we have a system of pulleys. And again, we have a hanging mass, so a way to produce a constant force through the weight of this thing. Force is then transferred through the string tension to the axle underneath this turntable, and the string is wrapped around the axle at a constant radius because it's flush to the surface of the axle. And so then that string tension gets turned into a torque at the axle and exerts a torque on this moment of inertia. Then by measuring the acceleration of the system, you're going to see a linear acceleration here. The pulleys will spin, and the torque here will provide an angular acceleration of the moment. And by measuring those, you can calculate what this moment is, even if you don't know it. So here's our setup. As you can see, I've got the turntable down here and a couple of pulleys. There's a mass hanger up here, hanging on a string that's wrapped around that top pulley. And the string goes down, wraps this bottom pulley, and then finally comes to the axle underneath the turntable here. Now, when this data was recorded, this pulley has a photosensor in it. It was connected to a computer measuring the rotation rate, and that's used to calculate, using the rotation of the pulley and its radius, you can calculate the linear speed of whatever the string is attached to. And so that's what we're going to be doing today, looking at the linear speed of the hanging mass. And down here, when I move this block out of the way, this is sort of held by friction right now, but when I move this out of the way, the turntable will be free to rotate and will undergo an acceleration due to the torque on this string. So let me show you that right now. So, by analyzing the dynamics of the system with a known hanging mass, supplying the force that's turning into the torque here, you can measure the acceleration and deduce the moment of inertia of this turntable. Once you've done that, you can take some other object, put it on there, repeat the experiment, measuring the acceleration, and then from that, deduce the moment of whatever object you've put on there, analogous to putting some extra mass on the cart in the air track experiment. once we've characterized the system, we can use it to measure moment of inertia.